What's up, everybody? Welcome back to another live stream. This is 2 for today, so it's quite a lot, I know, but we are not doing SAT Khan Academy problems right now. What we are doing is we are continuing the ALEKS challenge, and the ALEKS challenge for the, let me just do a quick sound check here. All right, we're good. So the ALEKS challenge, if you guys aren't familiar, this is part 5 of all the ALEKS challenges that I've done so far. This is basically a challenge where I'm trying to go through the entire pre-algebra pie. So if you're not familiar with ALEKS, it's an online math curriculum program, which is amazing. We use it as a supplemental tool at the school where I teach in the Pacific Palisades. And it's a phenomenal teaching tool. And what I'm trying to do is I'm trying to basically take us through the entire pre-algebra pie, which is essentially the curriculum for most 6th graders. And so we're going by topic all the way through. Now, there's 630 topics, and I've currently gone through 119 of these topics. So today we're going to see how far I can go in the next 2 hours. We're going to give it the best shot possible and see where we get. This program has a tendency of slowing down after I complete 40 or 50 topics, which makes it difficult to keep going in one continuous stream. But we'll see what happens, and maybe it'll be kinder to me today. By the way, I've already begun chopping up the footage and putting it in individual videos on my YouTube channel, on this YouTube channel already. So if you want to check those out, you can see by topic, you can click on these videos, and they're all broken up into basically between 1 and 2 minute videos. And that's the eventual goal, is to have a full library, so anybody trying to complete this curriculum will be able to use these videos once they get to a topic and they get stuck, and boom, watch the explanation and can go from there. All right, so without further ado, we're 19% through. That's 119 topics. That's pretty cool. So I'm trying to make it all the way through. It's a lot of topics, a lot of explanations. Let's get into it. All right, so we're going to continue the path here, and let's see where we're at. So solving a 2-step equation with integers. Let's give it a shot. Okay, we've got 4 plus 4x equals 32. So the way we want to isolate x, we want to look at the numbers that are on the same side as x. We want to recognize that x needs to be isolated, meaning we want to get x completely by itself. So the way we do that is we first start by moving these 4s to the other side. So let's start first by moving, do we move this 4 or this 4 first? We always start by moving the 4 farthest away from the x first. So I'm going to move this 4. So how do I move it? Well, what's the relationship between this and this 4x term here? They're being added together. What's the opposite of addition, or how can I get this gone and turn it into 0? We subtract 4, but we have to do it to both sides. It's got to be a balanced move. So we subtract 4 from both sides. 4 minus 4 is 0. 32 minus 4 is 28. So now I have 4x equals 28. So now I look again, I want to get rid of this 4 now. And how do we get rid of it? Well, what's the relationship between these two? The 4 is multiplying the x. What's the opposite of multiplication? Division. So I'm going to divide both sides by 4. Divide both sides by 4. 4 divided by 4 is 1. 1 times x is just x. And then 28 divided by 4 is 7. So we're left with x equals 7. Let's give that a shot and see. And we are good. All right, let's go on to the next one here. We've got negative 11 equals 2v minus 5. Okay, same thing here. We've got a 2 and a 5, or actually a negative 5, that are on the same side as the variable. We want to get rid of both of them. So first of all, how do we get rid of this 5? Well, we want to, it's a negative 5, and it's actually being subtracted from the v. So what's the opposite of subtraction? Is addition. And if you're confused about that, you just want to make sure whatever you're doing, it's going to zero out that 5 or make it disappear. And this will definitely work. We're going to add 5 to both sides. A negative 5 and a positive 5 combined to be 0. Negative 11, positive 5 equals negative 6. So negative 6 equals 2v. And then we got a 2 multiplying the v. We need to get rid of that. We do the opposite of multiplying by 2, which is dividing by 2. Divide both sides by 2, and we get v equals negative 3. And that's our answer for this guy. Okay, let's do one more. All right, we've got 5 equals negative 7 plus u over 3. All right, so first, what do we get rid of? The negative 7 or the 3? The negative 7 is farther away. Let's get rid of that first. Now, it is being added, okay, to this. So we might say, based on the last logic, based on the last rationale, we would subtract negative 7 from both sides. And we could do that. we can subtract -7 from both sides. But just recognize that subtracting -7 is the same as adding 7. And if we add 7, you think about it, it's the same thing, but it makes it a little easier if you think, well, combining a positive and a -7 goes to 0. And so we know that's going to work. So we add 7 to both sides. We get 12 equals, what is that, u over 3. And now we just need to get rid of this 3. What's the relationship between the u and the 3? The u is dividing the 3. What's the opposite of division? Multiplication. So we multiply both sides by 3. Multiplying and then dividing by 3, that cancels out to 1. So again, we've isolated u because 1u is the same as u. And then 3 times 12 is 36. And there's your answer. You can always take this answer and plug it back in and verify. Like, plug it into the original equation. 36 divided by 3 is 12. 12 plus -7 is indeed 5. So that's a great way to check your work if you're not sure. And in fact, it's a good habit to do it regardless. All right, let's go on to the next one. One down. Whole number division with decimals. Let's just double check. Whole number division with decimal answers. Okay. 26 divided by 8. So how do we do this? So we know we're going to get into the decimals. So we can just set it up where we can always add zeros after the decimal point when we're doing long division. And then everything after this point right here will be decimals. And we can just go ahead and put a decimal point up here because the decimal dots, the dots always line up. And now we can go from here. So 8 goes into 26 3 times. 3 times 8 is 24. We subtract this and we get 2. Bring down a 0. 8 goes into 20 how many times? Twice. 2 times 8 is 16. We subtract 20 minus 16 is 4. Bring down the 0. 8 goes into 40 5 times. 5 times 8 equals 40. And now we got no remainder. That means the decimals end right there, and we are done. So the answer here is 3.25. All right, cool. Let's go on to the next question. We got 2 divided by 5. So same thing, 2 divided by 5. I'm going to set it up like this. And I'm going to add a couple decimals just in case. We may not even need to go that far, but let's do it just in case. Now, we can't divide 2 by 5. We can divide 20 by 5. So 5 goes into 20 4 times. 4 times 5 is 20. We subtract, and we are done. So our answer right here is just 0.4. Put a 0 in front as a convention, and we're good. Last question. 1 divided by 4. I'm going to add a 0.00 just like this. Now 4 goes into, can't go into 1. 4 goes into 10. Oh, let's make sure to put the dot on top. 4 goes into 10 2 times. 2 times 4 is 8. We do a subtraction. 10 minus 8 is 2. Bring down the 0. 4 goes into 20 5 times. 5 times 4 is 20. And there we go. We got no remainder. Our answer is 0.25. Or 0.25. All right, let's keep going. Multiplication of 3 or 4 integers. All right. Now it's really important when we look at these integers, we need to recognize the rules for multiplying positives and negatives. So I always think about it as a light switch. You multiply a positive times a positive times a positive, it's going to be a positive answer. You throw one negative in the mix and it contaminates everything and it makes the whole product become negative. But you get the only way to undo that negative is get another negative in the mix. So if we have 2 negatives multiplying each other, they cancel out, it becomes a positive again. But now what if you have a third negative? It infects it again, goes back to negative. So let's look at this answer here. And the first thing is we want to figure out what is the final sign going to be. And we can see that we've got a negative and another negative. These two are going to cancel out and make it, and they're going to become positive. But then that third negative is going to mean this entire thing is contaminated again. Therefore, it is negative. Now let's do the actual multiplication. 4 times -4 is -16. Okay. Right? And then we've got -16 times -1. That's +16 times -3. +16 times -3. Boom. Infects it again. And we got -48. All right. Let's do the next one here. Now we got -2 times 2 times -1. All right, so let's do a step by step. First of all, we got how many negatives in the mix? We got 2. Those 2 are going to cancel out. We know our final answer is going to be positive, but let's do it step by step. We got -2 times 2. That becomes -4. And then we got, because right, that negative infects this positive, makes it a negative. But now we got -4 times -1. The negatives cancel out, and we get a +4. There we go. +4 and done. All right, and this last one, it's the same deal as the first one. We got 3 negatives, so let's write it out quickly. -2 times -1 is +2, right? These negatives cancel out. Then we've got 2 times +4, which is 8. And then 8, see, I'm going left to right. 8 times -4 is -32, because the negative contaminates the positive, and we got a -32. All right, cool. Let's keep going. Square root of a perfect square. Square roots ask a very interesting question. They ask, in this case, what number times itself equals 16? You can do a little guess and check if you're not sure. 2 times itself is 4. That doesn't work. 3 times itself, 9. That doesn't work. 4 times itself equals 16. Therefore, the square root of 16 is 4. All right, let's do one more. The square root of 36 is asking the question of what number times itself equals 36. The answer is 6, because 6 times 6 is indeed 36. All right, I'm going to do the last one fast. Square root of 25 is, of course, 5. Continue my path. Computing the distance between 2 integers. Okay, if we're trying to find the distance between 2 integers, this is just a subtraction problem. So what we got to do is take the bigger number and subtract the smaller number. We always got to do it that way, because distance is a positive number. It's not going to be negative. So we could do it the other way, 3 minus 10, but we'd have to take the absolute value. So instead, it's make life easy. Subtract the smaller from the larger. So we do 10 minus 3, which of course is 7. If you also wanted to count it out, you could see it's 1, 2, 3, 4, 5, 6, 7. So there's 2 ways to approach this problem. Let's do the next one. Now we've got -2 and a -8. So it's the same thing again. A little trickier with negatives, but it's -2 minus -8. All right, so what do we do when we have a minus and negative? Remember, that combines to become a plus. So it's -2 plus 8. When we have a negative and a positive being added like this, it's like a subtraction problem. It's really 8 minus 2. And since the positive is the bigger force, we know that final answer's got to be positive, and we're going to get a 6. If you're not sure about that, you can just count again and say it's 1, 2, 3, 4, 5, 6. So it's definitely a distance of 6. Cool. All right, last question. We're going to do 4 minus -5. So again, we have a minus and negative. That becomes a plus. So 4 plus 5 equals 9. And our answer is 9, just like that. There we go. All right, let's keep it going. Identifying congruent shapes on a grid. Which pairs of figures below are congruent? So what does congruent mean? Congruent is a fancy way of saying 2 things are equal. So which ones of these are congruent? Does that circle look like that exact same circle here? Yeah, it does. 4 across, 4 up and down. Same diameter. So I'm going to say these are congruent. Does this look to be congruent to this shape? Yeah, they look to be equal, right? We got a length of 1 here. Comes down like this. Down 3 over 1. Comes across by 4. These guys look congruent. So yes. Scroll down here. Are these congruent? No. They're similar. Like they're both triangles. And they look like they have similar dimensions. Like they're proportionate. But they're not equal. Congruent, again, is equal. Are these guys congruent? Looks like it, right? A length of 4. A width of 3. Same for both. Both rectangles. Let's see if that's correct. All right, let's move on to the next one. All right, are these guys congruent? Are these guys equal? No. Are these guys? Clearly not. These guys, they are not in the same orientation, but they're the same shape, same side lengths and everything. So I'm going to say yes, and same with these guys are also yes. All right, let's do the next and last one. These two are equal, therefore they are congruent. Clearly not. This one is right. It was way bigger, almost double the size. These are definitely not congruent, right? If you're not sure, you might be confused because you might be like, well, wait, this is 4 across and that's 4 across. This is actually not 4 across. This is actually, let's see, 16, this is the square root of 32. It's longer because it's going diagonally. And you can kind of see this triangle is bigger than this one. So these are not equal. And these shapes, this is a pentagon versus a quadrilateral. Definitely not. Let's check that. All right, there we go. Let's keep going. All right, product of a fraction and a whole number. Here we go. Write your answer as a fraction in simplest form. So when we are looking at multiplying fractions against whole numbers, you got to think about that whole number not as a whole number, but as a fraction, because every whole number is simply itself over 1. So we've got a fraction of 4 over 15 times 10 over 1. Now, you can go ahead and multiply this out like this, 4 times 10, 15 times 1, but it's better to usually cross-simplify, meaning let's see if we can divide numbers on the top and bottom by the same number, a common factor, and we can. 10 and 15 can both be divided by 5. So if I divide 10 by 5, I get 2. If I divide 15 by 5, I get 3. And that's the balance. If we're doing something to the top, overall, we had to do something to the bottom as well. It doesn't matter that they're separated. They've now combined because they're as one giant fraction because of the multiplication. Now it's most simplified. Now we can multiply across. We get 4 times 2 on the top, 3 times 1 on the bottom, and we get 8 over 3. Now we want simplest form. They may accept this as an improper fraction, but usually simplest form means a mixed number. So how do we convert it to a mixed number? We see how many times does 3 fit into 8? It fits in it 2 times. And then what's left over? Well, 3 goes in once, twice. That's 6. So we pull a 6 out of the 8, and what's left is just a 2 over 3. So this reduces to 2 and 2/3. All right, let's do the next question here. We've got the same dealio, 4 over 21 times 7 over 1, straight away converting it to an improper fraction over 1. Let's cross simplify. The 21 and the 7 can both be divided by 7. 7 divided by 7 is 1. 21 divided by 7 is 3. And now we multiply across. 4 times 1 and 3 times 1, we get 4 over 3. And again, same thing to simplify this or turn it into a mixed number. 3 goes into 4 once. And then what do we have left over up here? Well, we just have a 1 remaining. Remainder of 1 if we did that division, and that's what stays over the 3, and so it's 1 and 1/3. All right, let's keep going. Last one. 9 over 1 straight away, just putting it over 1 times 2 over 15. Now let's cross simplify. 9 and 15 can both be divided by 3. 15 divided by 3 is 5. 9 divided by 3 is 3. Multiply across, multiply across. We get 6 over 5. How many 5s fit into the 6? 1, with a remainder of 1. And if 1 stays over that denominator of 5, so we have 1 and 1/5. All right, continue. Decimal multiplication problem type 1. So we got 6.57 times 20.9. Okay. Do the decimals have to be lined up for multiplication? No, definitely not, and that's the beauty of it. So I'm going to show you how to tackle this. First, you just treat it like any other multiplication problem. So we're going to do step by step. First, we're going to multiply the 9 by everything, then the 0 by everything, and then the 2 by everything. So let's start here. 9 times 7 is 63. Carry the 6. 9 times 5 is 45. Plus 6 is 51. Carry the 5. 9 times 6 is 54. Plus 5 is 59. Now we go down here, we come across the 0. We start with the 0. But then 0 times 7 is 0. 0 times all these is just 0, 0. So this row is kind of unnecessary, but we'll just put it in for good form. And then to get to this guy, right? Well, there's 2 places that we're moving over, so we add 2 zeros. And now we continue the multiplication. Let's get rid of this too. 2 times 7 is 14, carry a 1. 2 times 5 is 10, plus 1 is 11, carry a 1. 2 times 6 is 12, plus 1 is 13. And now we add them all up. We've got 3, 1, 9 plus 4 is 13, carry a 1. 1 plus 5 is 6, plus 1 is 7, 3, and 1. And we've got 1, 2, 3 numbers behind the decimal point. So this is the really important part. If we want to figure out where do we put the decimal, we count the number of digits to the right of the decimal in this multiplication problem. We got 1, 2, 3. Therefore, we move the decimal 1, 2, 3. And our final answer is 137.313. I always do a quick gut check. Does that make sense? It's about 20 times 6, which is 120. This seems roughly right to me. Let's give it a shot. All right, cool. Let's do one more. 6.09 times 9.56. Okay, let's go. 6 times 9 is 54. Carry the 5. 6 times 0 is 0, plus 5 is 5. 6 times 6 is 36. Oops. 36. Next line here, we go 1 to the right, to the left, therefore we add a 0. 5 times 9 is 45. Let's cross this out. Carry the 4. 5 times 0 is 0, plus 4 is 4. 5 times 6 is 30. Now we're going to the 9. 1, 2. So we got 1, 2 zeros. 9 times 9 is 81. Carry the 8. 9 times 0 is 0, plus 8 is 8. And then 9 times 6 is 54. Now let's add these guys up. 4. You see how important it is to keep everything nice and organized to make sure we don't make any mix-ups. 5 plus 5 is 10. Carry the 1. 1, 7, 11, 12. Carry the 1. 4 plus 8 is 12. Carry the 1. 1 plus 3 plus 4 is 8. And then 5. How many decimals do we have? We have 1 digit, 2 digit, 3 digit, 4 digits to the right of these decimals. Therefore, we're going to move it once, twice, 3 times, 4 times. Final answer is 58.2204. Nice. All right. Last one. 0.74 times 45.6. Do I want to, is it important that I include that 0? It really isn't. In fact, I think it's pointless to do that because then you feel tempted to multiply through. You're going to get all zeros. It's to the left of the decimal place, so it makes no difference, has no bearing on where you place the decimal. I wouldn't even include it. So let's start here. 4 times 6 is 24. Carry the 2. 4 times 5 is 20, plus 2 is 22. Carry the 2. 4 times 4 is 16, plus 2 is 18. Now we start with 1 digit over, so we add a 0. 7 times 6 is 42. Whoops. Carry the 4. 7 times 5 is 35, plus 4 is 39. Carry the 3. 7 times 4 is 28, plus 3 is 31. Now we add them all up. 4, 4. 8 plus 9 is 17, plus 1 plus 1 plus 1 is 3, 3. And how many digits do we have to the right of the decimal? 1, 2, 3. So we move the decimal once, twice, 3 times. And there's our answer, 33.744. That's it right. All right, sweet. Those are tricky because you can easily make a silly mistake or a few silly mistakes. It's hard to tell where you've gone wrong if you do such a thing. All right, interpreting a tally table. Karen asked her classmates to choose their favorite flavor. She ended up with the tally table below. How many students chose vanilla? How does a tally table work? Each one of these hash marks represents one person, usually. I mean, it could say otherwise, but we're going to assume that each one represents one person. And when we have a cross, so you can count like 1, 2, 3, 4. What does this diagonal one mean? That's just how we represent the 5th one. We could write it like this. And we could continue writing hash marks like that, but it gets confusing. It's hard to count. So the convention is once we do 4, the fifth one is going like this. And then we can look at these little packets as 5. So it's easier to count. So for example, if I looked at chocolate and wanted to count chocolate, I'd be like, oh, 5, 10, 1, 2, 3, 4, 14. So now let's look at vanilla. How many students chose vanilla? It's just one of these nice packets of 1, 2, 3, 4 in a diagonal, which is 5. So the answer is 5. All right, let's go to the next one. So now it says, Aldo asked his classmates to choose their favorite fruit. He ended up with the tally table below. How many students chose bananas? So now let's look at bananas. We don't even have a full packet with a diagonal hash mark. We got 1, 2, 3, 4, right? So we can put 4 people chose bananas, and that's it. Last one. Lucy asked her classmate to choose their favorite color. How many students chose orange? We've got one packet of 5 plus an additional 1, 2, 3, 4. So 5 plus 4, a total of 9. All right, let's keep going. All right, now we're talking about exponents, and we're talking about powers of 10. So rewrite as a power of 10. What's the shortcut to doing this? Well, this is 10 to some power, but what is that power? Well, let me show you by way of demonstration. What's 10 squared? 10 squared is 10 times 10, which is 100. 10 cubed, whoops, is 10 times 10 times 10, right? 3 tens, which equals 1,000. So what do you notice here? We notice that this exponent corresponds with the number of zeros in the final answer. So if we want to rewrite this with an exponent, we've got to count the zeros. We got 1, 2, 3, 4, 5, 6, 7, 8 zeros. Therefore, this should be written as 10 to the 8th. 10 to the 8th power. All right, let's go on to the next one. Let's count these zeros. So now they want us to evaluate this. Well, how would we write this out? If we evaluated it, let's use that same logic. 10 to the 4th, this is going to correspond to the number of zeros in the final answer if we evaluate this. So it's going to be 1, 2, 3, 4 zeros. So that's 10,000. I think they want a comma usually in there. All right. And last one here. Write this as a power of 10. So again, count the zeros, and that's the number. That number is going to go in the exponent position. So we got 1, 2, 3, 4, 5, 6, 7. So we got 7 zeros. So this is 10 to the 7th power. All right, cool. Continue the payoff. All right, ordering decimals. So we have let's do it like this. 1.12, 1.102, 1.5, and 1.1211. So what am I doing? I'm lining these all up by the dots. And so we can see from digit to digit to digit to make a comparison. And I'm going to round these out so they all have the same number of digits. How do I do that? Well, if it stops here, I can just add zeros. So they all have 4 digits after the decimal. And these zeros continue on indefinitely, but after this is pointless because they're all going to have zeros. It's not going to make for showing any significant differences. So now how do we determine which is biggest? Well, we go from left to right. First, we look in the unit spot and see if there's any number that's bigger than the others. No, they're all equal to 1. So this doesn't help us, right? We kind of move past that. Then we go to the 10th spot. We look for the biggest number here and check it out. I see 1.5. So that means this is number 1, right? So at this point, this guy dominates, and that's the first digit that we've seen a difference. This is the biggest. All right, cool. Now we're only looking at these 3. So now let's go to the next digit. We got a 2, a 0, and a 2. Well, we've got a tie now between here and here. How do we do the tiebreaker between these two guys? We got to go to the 1,000th spot. Okay, this guy's not even in the running anymore because it's smaller than both of these. So what does that tell us? This is smaller than this and this. Therefore, this is my 4th place winner. Let's knock him out. Now it's between who gets second. So they're equal here. Let's go to the next digit, to the thousands place. We got a 0 here. We got a 1 here. So this guy wins. It's coming in second. And of course, third place goes up here. So if we were to put it, this is again the biggest, right? The crocodile, the alligator mouth eats the biggest number. So 1.5 over here. 1.1211 over here. That's second place. Third place is 1.12, and fourth place is 1.102. All right, let's see this guy here. 5.205, 5.2. I'm going to round it out with more zeros. 4.189. Add zeros here to make those equal. You see how I'm being very careful with my placements. And then 5.25 and add 2 zeros. All the dots are lined up nicely. Now let's do our comparison. We got a 5, 5, 4, 5. Okay, so right off the bat we see a difference here. This is clearly smaller than these two guys. These rest of these digits don't even matter because this one is smaller than all three. We already know fourth place goes here. Now let's look at these guys. We got a three-way tie for first. Let's go to the next one, see if this tie breaks it. We got a three-way tie again for first, 2, 2, 2, so there's no discernible difference. Go to the next column, 0, 0, tie again, but then a 5. So this is the biggest because this is the first time we have a discrepancy, and it's for this guy. Therefore, we already know this guy's number 1. And now we're just comparing against these two. We're looking to see who comes in second place. So we know 5s match up, 2s match up, 0s match up, and now we get to the thousands digit. We see a difference. We see a 5 up here, a 0 up here. Therefore, this guy's bigger. This guy gets the second place, and this one gets third place. And now let's translate it over here. 5.25 is our winner. This guy is in last place, so we'll put him all the way there. Then we've got 5.2 is in third place right here, and 5.205 right there. All right, cool. This last one, I'm just going to blaze through it. So 2.49, clearly the biggest. Then this guy, then this guy, then this guy. All right, division of a decimal by power of 10. So we don't really have to do much here. I mean, we can set up a division problem. If you're ever confused by this, you can set up a division problem and divide by 100 and go through that whole process. But there's a shortcut, okay? When we divide something by a power of 10, we just look again at the number of zeros we're dividing by. And the number of zeros, since it's 100, tells us how many places we move the decimal to the left. So if it was 33.5 divided by 10, since there's 1 0, it becomes, boom, the decimal moves 1 spot to the left, which becomes 3.35. But here we're dividing by 100. So we move the decimal 2 spots, 1, 2, and our answer is 0.335. 0.335. Oh, they wanted a 0 in front. Yeah, I forgot about that. And now let's look at the next one. We've got 3.84 again divided by 10. How many zeros are there? Just 1, which means we move the decimal spot once to the left. Final answer is 0.384. Don't forget the 0 in front. 0.384. Last but not least, dividing it by 1,000. So how many spaces do we move it? Well, how many zeros are there? 1, 2, 3. So again, we're dividing by 1,000, so we move the decimal to the left 3 spots. So it goes 1, 2, 3. But what happens with this empty space? Well, we got to fill it in with a 0. So our final answer is 0.0819. All right, cool. classifying likelihood. So this is probability. So picking a white marble in this bag, what is likely? Well, let's talk about all these different classifications. So we've got certain, likely, unlikely, impossible. Impossible means there's no way we could choose a white marble. Well, clearly there's white marbles in there, so it can't be impossible. What does unlikely mean? Unlikely, we usually characterize that as a less than 50% chance, less than 1 out of 2. Well, it looks to me like we got 1, 2, 3, 4, 5, 6 white marbles out of 7 total. Is that unlikely? No, we got a 6 out of 7 chance. That's much bigger than a 1 out of 2 chance. This is a much larger fraction. Therefore, we can definitely say this is not unlikely. Is it likely? Yeah, it's definitely likely. But where would it be? How would we cross over into certain? Certain would be if every single marble in here were white. So picking a white marble, we would definitely do it because there's only white marbles. So this goes in the likely category. Let's talk about this one. Picking a white marble here. Well, how many marbles do we have? We have 7. How many marbles are white? 1 out of 7. So it's not impossible because we could pick a white marble. Unlikely, what did I say is the test? Is it less than a 50% chance or half? Yes, it is. 1 out of 7 is less than half. So therefore, we'll put that in the unlikely category. More likely to pick gray or black. And then picking a white marble here. How many marbles total do we have? 7. How many white marbles? We got 0. The probability is 0. This means it's impossible. There's no way we could pick this 1,000 billion trillion times, pick a marble out of the bag. We'll never get a white. It's impossible. All right, picking a black marble here. Well, every single marble is black. There's no way we're going to get anything other than a black marble. This is certain. Picking a black marble here is we've got 2 black marbles out of a total of 6 marbles. We got to count every single marble. So that's cool, but is that less than a half? Well, a half would be 3 out of 6. So this is less than a half. This is, I'm going to put it in the unlikely category. It's not impossible, but it's less than that 50%, so it's unlikely. What about here? Picking a black marble. Here we've got 4 black marbles out of 6 total. That's greater than a half. That's greater than 3 out of 6. Therefore, I'm going to put this in the likely category. Certain would be if they were all black like we have in this first one. Okay, let's keep going. All right, let's blaze through this. Gray marble, this is likely, more than half. Certain, because they're all. Gray marble is less than half, but not impossible because there's still a couple. All right, let's keep going. Fraction, addition. Okay, 7/12 minus 5/12. So let's see, we got 7 minus 5. So when we're subtracting fractions, they have the same denominators. We don't mess with the denominators. The denominators just stays the same. But it's important because this just tells us the total that we're, like the total potential or capacity. Like with a pizza, we're not actually subtracting the 12 slices. We're just saying the pizza came with 12 slices, and that's the total potential amount of pizza that there could be in a pizza. So what we actually have is 7 parts. What we actually have here is 5 parts. So we're just subtracting the parts. 7 minus 5 is 2. This is 2/12. But what are we doing here? Now we got to simplify this. The way we simplify is we look at this final fraction and say, can we divide the top and bottom by the same number without getting a remainder? We can divide 2 and 12 both by 2. So we divide 2 by 2 and 12 by 2. 2 divided by 2 is 1. 12 divided by 2 is 6. Our final answer is 1/6. Let's go on to the next one. We've got 7/18 minus 5/18. Again, we're going to subtract the tops. Denominator stays the same. 7 minus 5 is 2. Then we can divide the top and bottom by 2 again. And we get 2 divided by 2 is 1. 18 divided by 2 is 9. 1 over 9 is equivalent to 2 over 18. We're just putting it in the simplest form possible. All right. Now I'm going to blaze through this guy. 3 nines. Actually, I'm going to explain this one because it goes over 1, so that's important. So we have 3 tenths plus 9 tenths. Again, add the top. Denominator stays the same. 3 plus 9 is 12. So first let's simplify by dividing the top and bottom by what we can. We can divide the top and bottom by 2. Both even numbers. 12 divided by 2 is 6. 10 divided by 2 is 5. But now we have an improper fraction. So how do we convert this to a mixed number? Well, how many 5s can we extract from that 6? We can extract 1. And what's left over when we pull that 5 out? We've got a 1 left over. So the final answer is 1 1/5. All right, cool. Let's keep going. Using a calculator to convert a fraction to a decimal. Let me just double check this topic. Converting a fraction with the denominator of 100. No, using a calculator to convert a fraction to a rounded decimal. So the calculator, you can see that the calculator app is unlocked for this one, which is pretty nice. So we write this as a decimal rounded to the nearest tenth. So remember, the top number, when we look at a fraction, 28 over 23, this is just a division problem, suspended. So this is actually the numerator divided by the denominator, and that's all this is. And so we just got to carry out that division problem. So it is, 28 divided by 23, and they write it just like that as a fraction. Same thing, we hit enter, and we get this crazy thing here. But they said round to the nearest tenth. Here's the nearest tenth value. So how do we round? Well, we look to the digit 1 over, which is the hundredth spot. If it's 5 or greater, this 2 bumps up to a 3. If it's less than 5, like between 0 and 4, the 2 just stays the same and everything goes away or goes to 0. So we can, since it's 1, boom, this whole thing drops off and we're left with 1.2. Okay, let's go to the next one. All right, we're rounding this to the nearest hundredth. So now we have 9 divided by 17. Where's the hundredth spot? So we got 0.5. That's the 10th spot. Here's the hundredth spot. If we want to round to the hundredth spot, we got to look at the thousandth spot. So is this thousandth spot, is it 5 or greater? Yeah, it's 9. So if we're rounding to this spot, this pushes that 2 up to a 3. And everything else zeroes out. So we're left with 0.53. All right, last one, 19 divided by 22. Whoops. And this is the nearest tenth, 19 divided by 22. So again, here's my 10th spot, which is 8. The digit to the 1 spot over is the hundredth, and it's above 5, which pushes that 8 up to the next integer, which is 9. So this ends up being 0.9. Cool. Writing an equation and solving a multiplication problem, it looks like. Okay. All right, Rachel made 72 hats. Rachel made 9 times as many hats as Dale. Let H be the number of hats that Dale made. Okay. So Rachel made 72 hats, which is 9 times as many hats as Dale. Therefore, it's 9 times D. I'm using parentheses to signify multiplication. You could also put an X in here if you want. That's what they're doing here. Just trying to get people out of the habit of using X for multiplication. So it's 72 equals 9 times D. Or if we, sorry, they're using H to represent the number of hats Dale made. So let's get rid of this and let's replace it with an H. And now now they want us to represent it down here. Well, I did it backwards. The way that they wanted is the multiplication problem on the left, but it's the same thing. So we have 9 times H, and they're telling you everything to use equals 72. So they're kind of helping you set this problem up. And then if we want to find H, what did I say before? We're trying to isolate a variable, trying to isolate H. We need to get all these numbers out of here. So right now we got a 9 on the same side. We need to get rid of it. How do we do that? Well, we see what's the 9 doing to the H? Multiplying. The opposite of that is dividing. So we divide both sides by 9. 9 divided by 9 is 1. So now we're left with H alone here. 72 divided by 9 is 8. Therefore, H equals 8. And if you were to plug that 8 back into this equation, we get a true statement. We get 9 times 8 equals 72, which of course is true. Okay. Raina wrapped 15 gifts. Raina wrapped 5 times as many gifts as John. And N is the number of gifts that John wrapped. So let's think about it like this. What's going to happen with these values? Again, 15 is this total here. That's what Raina wrapped. And that's 5 times as many as John. So we kind of use the language of representing 5 times the amount that John wrapped, 5 times N, and now we got our equation. 15 equals 5 times N. And again, if we want to solve for N, I'm going to write it like this. 15 equals 5 times N. We need to isolate the N, meaning we need to get this 5 out of here. The 5 is multiplying. The opposite of that, or the inverse operation, is dividing both sides by 5. So we do 5 divided by 5 here. That's 1. And we get N equals 15 divided by 5, or N equals 3. All right, cool. All right, I'm just going to blaze through this one. 27. Cool. All right, let's continue. Finding x and y intercepts given the graph. Okay. All right, first of all, what is an x-intercept? What is a y-intercept? We think about the word intercept probably because you hear it in football. It's kind of you intercept a pass. You come in the path of the pass, you take the ball. So same thing. We're talking about where does this line come into the path. Y-intercept means where does it hit the y-axis. X-intercept means where does it hit the x-axis, okay? So if we look at this line, the x-intercept occurs at -3. Right there. What about the y-intercept? The y-intercept occurs at this point at 2. Not sure if we have to do this in coordinate form or if it just wants a singular answer. Let's try this and see what it says. Yeah, that's fine. So otherwise, the other way you could write it is the coordinate for the y-intercept is simply 0, 2. And the coordinate for the x-intercept is -3, 0. That takes into account that actual point. But they are cool with this, so let's just roll with that. All right, here we go. X-intercept, where does it hit the x-axis? Right over here at 4. Y-intercept, where does it hit the y-axis? Right over here at 1. That none box is there in case it doesn't ever hit one of the axes, which hopefully we'll see an example, I presume, in the next problem. All right, here we go. Perfect. So the let's talk about these intercepts again. The y-intercept, where does it hit that? Right there. That's a -2. It's hard to see the negative, but it's a -2. It's below the x-axis. Where does the x-intercept happen? Well, it doesn't happen anywhere here. Does it happen somewhere off the grid? The presumption is it does not, because this is parallel to the x-axis, so at least it looks parallel. And so therefore we are to assume that it will run next to it, but will never actually hit the x-axis. So in this case, there's our chance to use the none value. Okay. Measuring an angle with a protractor. So this protractor can be a little glitchy. So anyway, it says use the protractor to find the degree measure of the angle. So this is how you use a protractor. So we start here. We want to make sure to get this point, the center of the protractor, right lined up with this point here that is where the angle is made, right at that point. Then we want to wrap this around and have one of the sides be lined up with this side of the protractor. We could also do it like this too. Doesn't matter. But in this case, it's better to do it with the 0. If we did it here lined up with the 180, we'd have to subtract 180 and that value. But this makes it a lot easier. Okay, so now we've got it laid down nicely. And all we got to do is see, where's the second line, where does it point to? Well, it's not pointing to 100, it's not pointing to 110, it's pointing right in between those, so the presumption is that is exactly 105. It's not labeled, but that's what's in the middle of 105 and 110. Put our little degree marker there. That signifies degrees. And done. Let's move on to the next one. All right, use a protractor to find the degree measure. Same deal. So first we're going to place it right there. Now we're going to line this up here. You see how this is nicely lined up with the 0. I'm going to tap it again. And so what is this degree measure? Well, let's just look where this one points to 0. What does this one point to? This one points right on 140. So that's really clean and neat. Don't have to question that. Okay, let's do one more. Boom, right at that point. Let's bring it over here. This one's on the 0, and therefore this is our final answer. It's in between 40 and 50. It's at 45. Oops, I'm having trouble hitting this. Hold on. Boom. Cool. Let's keep going. Oh, whoops. My bad. What am I doing here? All right, here we go. Constructing a bar graph for, let's read the full thing. Constructing a bar graph for non-numerical data. It's starting to glitch. So this tends to be a common thing with this program. It starts to glitch at this point, so we'll do our best to keep it moving. The ice cream dessert at a restaurant comes in 4 flavors: chocolate, peanut butter, lemon, and cookie dough. There were 13 ice cream desserts ordered on Friday. Here they are by flavor. Okay, so now they're kind of listing all this out here. So we want to represent this in terms of the count of each of these. So let's try and do this one by one. So first of all, let's count the number. Let's look at lemons. I see lemon first. Let's just count the number of lemons we see in this list. We got 1 lemon, 2 lemons, 3 lemons, and 4 lemons. So what does that mean? That means I'm going to graph lemon 4 times. Okay. Now remember, all of these values down here need to add up to 13 because we got 13 desserts ordered in total. That's going to be our way of checking our answers. Now let's look next. I see peanut butter next. Let's count the peanut butters. We got 1, 2. I only see 2 peanut butters, so we're going to get 2 values here. Now what about cookie dough? We got 1 cookie dough, 2 cookie doughs, 3 cookie doughs, 4 cookie doughs. Now, I could go right ahead and say, well, I know there's 13 total. This adds up to 10. Therefore, there's got to be 3 chocolates. Don't do that. Be careful and count them out because then that's your way of verifying did you make a mistake with some of these other counts. So let's look at chocolate. I see 1 chocolate. No, sorry, 1 chocolate, 2 chocolates, 3 chocolates. That's what we predicted. That's what we wanted to see. I feel pretty confident that this is correct. Cool. All right, same idea. The drink, so we have 4 types of drinks: orange juice, root beer, apple cider, and iced tea. We got 16 students. Here are the results. Let's go for it. First, let's count root beer. We got 1, 2, 3, 4, 5, 6 root beers. Let's look at next is orange juice. We've got 1 orange juice, 2 orange juices, 3 orange juices, 4 orange juices, and 5 orange juices. So a really careful way to do this would be to write all these down and cross them out as we kind of go through to make sure we don't make any mistakes. But since it would take such a long time to copy this, I'm trying to do my best to do it just from looking at it. You could copy and paste this or something. I wouldn't want to rewrite all of this. That'd take a long time. Now let's look at apple cider. I see 1 apple cider, 2 apple ciders, 3 apple ciders, and now iced tea. We got 1 iced tea, 2 iced teas. So what do these need to add up to? 16, right? We had 16 students. So 5 plus 6 is 11, plus 3 is 14, plus 2 is 16. Cool. Let's do the same thing. I'm going to do this one. I'm going to blaze through this one. 14 shirts. So we got blue. We got 1, 2, 3 blue. We got 1 white. We've got yellow. We got 1 yellow, 2 yellows, 3, 4, 5, 6, 7 yellows. And we got 1 red, 2 reds, 3 reds. 3 plus 7 is 10, plus 3 is 13, plus 1 is 14. So this looks good. All right. Okay, let's talk about the reciprocals of numbers. So what does the reciprocal of a number mean? It means we're basically switching the numerator and the denominator. So how do we take the reciprocal of a whole number? First of all, remember that a whole number is 16 or whatever that number is over 1. So this is really 16 over 1. The reciprocal is we have the numerator and the denominator switch places. The 1 goes on top, 16 goes on the bottom. And that's our reciprocal. What about 3 over 5? That's a little easier because it's already in fraction format. This becomes 5 over 3. So we got 1 over 16 here, and this will stay as an improper fraction, 5/3. Cool. Let's go on to the next one. All right, so again, reciprocal of 4/1 and 5/6. For 4/1, these guys switch places and we get 1/4. For 5/6, they switch places and we get 6/5. So this becomes 1/4. This becomes 6/5. All right, same deal, 11/8. And I'm going to write that 5 as 5/1. Now let's switch it and switch it. And we get 8 on top, 11 on the bottom. And here we're going to switch these as well. And we're going to get 1/5. Over 5. Excellent. Let's keep going. Okay, writing a mixed number as an improper fraction. I'm going to show you the steps for how to tackle this. While this is loading, let me quickly look and see if there's any questions here. Nope, we are good. All right, 3 7/9. 3 7/9 as an improper fraction. So here's the shortcut. The explanation is 3 wholes means we're representing, we want to put this back into the fraction. So really that's 9/9, 9/9, and 9/9. So that's one way to think about it. We just add these guys up and then add it to this fraction. Okay, but the shortcut is this. The fastest way to do this is you take the whole number, multiply it against that denominator, 3 times 9, which is 27, and then you add it to the numerator, and you end up with 34/9. But if we were to do it this way, we get the same thing. We do 9 9s plus 9 9s plus 9 9s plus 7 9s, and we get 9 plus 9 plus 9, which is 27, plus 7, which is 34. Remember, when we add fractions, we don't add the denominators. The denominators stay the same. So both ways will yield the same answer, which means both ways are obviously legitimate. All right, let's keep going. Three and 3/5, same deal. I'm going to multiply the 5 by the 3. That becomes 15. We're going to add it to the numerator, and we end up getting 3 plus 15, which is 18/5. All right, let's do this last one quickly. 4 times 6 is 24, plus 5 is 29/6. Cool. Table for a linear equation. Now I'm noticing that this is really starting to slow down. I may be taking a break or stepping away a little bit early. I was planning to go for another 40 minutes, but this load time, it just really slows the progress down. So I may take a break, pause, edit all these videos, and then resume either later in the day or tomorrow morning. Y equals 6x minus 2. So we want to plug it in, and when we're filling out when we're doing this table, with this function rule, this is just a function, and we're figuring out for these values of x, what does y equal? Because remember, a function is just a relationship. So how do we do this? So again, 6x minus 2. To figure out all these values, we are plugging in these various x values. So first we're going to plug in a -5. Then we're going to plug in a -1. See, I'm just replacing the x. Remember, this is multiplication. It's not 65. It's 6 times -5. Y equals 6 times 0 minus 2. And y equals 6 times 1 minus 2. Okay, 6 times -5 is -30, right? The negative contaminates the positive. -30 minus 2 is -32, because these are, after all, both negative numbers, and when it's really a plus negative, so we're just combining, gets more negative, we get a -32. Here we get -6 minus 2. This is, again, a minus just means a plus negative. These are two negative numbers that are being combined to get us -8. 6 times 0 is 0 minus 2. 0 minus 2 is just -2. And then this is 6 minus 2. 6 minus 2 is 4. So the way we fill it in is for -5, we got -32. For -1, we got -8. For 0, we got -2. And for 1, we got 4. Let's go to the next problem. Okay, y equals -2x minus 5. Same dealio. We've got these different values, so let's write it out. Y equals -2 times -4 minus 5. Y equals -2 times -2. Whoops. -2 minus 5. Y equals -2 times 0 minus 5. And y equals -2 times 2 minus 5. All right, let's evaluate these. -2 times -4. Negative times a negative is a positive. So it becomes +8 minus 5, which is 3. Negative times a negative is a positive. +4 minus 5, which equals -1. Because this is really a +4 plus a -5, which is a negative value, -1. -2 times 0 is 0 minus 5, which is just -5. And finally, we got -2 times 2, which is -4 minus 5, which is a negative and a negative, which combines to be a greater negative of -9, right? It's like a -4 plus a -5, which is -9. So now let's put all these values in. We got 3, we've got -1, we've got -5, and we've got -9. This last one I'm going to blaze through. This is -3, this is 2, this is 7, and this is 12. Okay. All right, finding the missing length in a figure. Find the missing side length. We've got a figure. I'm going to reproduce it over here. So this is our x. We've got 4 over here. We've got 9 over here. We've got 6 over here. We've got 5 over here. And we got 13 over here. The important piece is that it says everything is a right angle. And that's important because that tells us that the total distance across on top has to equal this total distance on the bottom, which indeed it does. It's 4 going across, 9 going across. 4 plus 9 is 13, and those match. The same has to be true over here, meaning this total vertical distance traveled by this side and this side combined has to equal this total distance here. So since we have a 5 and a 6 going up, this distance therefore has to equal the sum of these two, which is 6 plus 5, which of course is 11. All right, now let's do the problem. Okay, first I'm going to reproduce this guy here. So we know that this side here is 16, this is 10, this is 5, this is 6, this is our x, and this is 4. Now, we know that because everything meets at a right angle, this total distance traveled across up top has to equal this total distance traveled down here by these two pieces. And it makes sense, right? That's what indeed is occurring. We've got a 6 and a 4. Add those up and we get 10, which is what we have up top. The same thing is true here. We've got 16 going all the way down. Here we've got an unknown value plus a 5 going up top. Well, since this 5 and this x combined need to equal this 16, we know that 5 plus x equals 16. We can therefore figure out that by subtracting 5 from both sides, we can figure out that x equals 11. And this is not feet squared, not feet cubed. This is just length, which is feet. All right, let's do this same problem here. I'm going to draw it out. So here's my x, here's my 16, and here's my 9, here's my 8, here's my 7, and 14. Okay, so look, we're looking at this horizontal distance across. So we know that this total horizontal distance going all the way across is 14. And we know up here, part of the way is 8. The remaining way is this x. Therefore, it stands to reason that 8 plus that x, this entire distance traveled horizontally up top, has to equal this total distance on the bottom, which is 14. Therefore, if we want to solve for x, we subtract 8 from both sides, and we get x equals 6. Oh, sorry, not 16. X equals 6. 14 minus 8 is 6. And again, that's feet. It's just a unit of length. Okay, this last one I'm going to blaze through here. We got this question mark. This is 5 plus 7, which is 12. Now we are comparing fractions with the same denominator. I think this might be my last one, and then I'm going to call it. It's just getting way too slow. All right. Here we go. Same denominator. When we are comparing fractions with the same denominator, it's pretty straightforward. We don't have to look at anything but the numerators, and we just find the biggest numerator. What has the biggest one here? The top part, it's the 8, then the 6, then the 5. Therefore, 8 is our largest. But look, remember, the biggest one is always the one that this alligator is eating, and this alligator is eating this guy. So the greatest one is going to go over here based on this orientation. The middle one is going to go here, and this is our smallest at the very end. All of these guys are pointing out here to the smallest. Same thing here. We got 3/8, 7/8, and 6/8. Our biggest one is obviously with the 7. Alligators are facing this one, so that's the biggest. 6 is our next biggest number, goes here, and 3 is the smallest. Cool. All right, let's blaze through this last one. 6 is the biggest, then 4, then 1. All right. So we got 4%, and I think we were at 119, so we got into 143. So that's 24 topics. It's okay. It's not the greatest. We're almost at that 25% mark. So we're going to leave it right there for today, or for now. I may do another live stream later tonight. Most likely we'll probably tackle it tomorrow morning. So make sure to check back in with us tomorrow. And I'm going to do my best. I'm going to try and make it through this as soon as possible. This still may take me another couple weeks, but my goal was to finish this before spring break ends. We'll see if I can do it. It's just going to take a lot of time and quite a few more live streams. So anyways, thank you guys so much for joining me today with this quest to get all these topics done, 630. So now we're at 100 and whatever it is, 43. That's pretty good. Almost at a quarter of the way through. Hope you guys have a great rest of your day, and I'll see you all next time. Take it easy.